Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study what is the stress-strain diagram of a ductile material. Here is when the beam is subjected to the tensile force, a deformation takes place, that is called increment in length, that causes to reduce in cross-sectional area. And in the case of compression strain, under compressive load, what will happen? The cross-sectional area of the structure or body or component will be increased and reduces in the length. Now coming to draw what is the stress strain diagram. The diagram which indicates the relationship between stress and strain. The diagram is known as the stress diagram. It is the tensile universal testing (UTM) universal testing machine. Under this testing machine, we can experiment, or we can test the component under tensile load at the same time, and also compressive load and shear loads also. There are 3 tests can be conducted in this universal testing machine. Now, the stress diagram is a plot of stress versus or strain. Here, the stress is the dependent parameter, and whereas the strain is independent. Now, the stress, when the stress is occurring, under what stress? The strain diagram. Now, here the diagram gives us the behavior of the material and also material properties. And each material produces a different stress strain diagram. Suppose if we conduct a steel, the stress strain diagram is different from the material of the copper. And each material having own stress strain, their own behavior. That behavior of the material can be studied by using from the stress strain diagram. The stress strain diagram can be drawn by using universal testing machine. Under the universal testing machine, when the load is applied, tensile load is applied, we can observe this stress strain diagram. The stress strain diagram for a ductile material seems like this. So here there are various components are there. Here we have to study what is the stress, what is the strain, and what is elastic region, what is plastic region. The region is the point 2 is called yield strength sigma y, and there are different points are there 0, 1, 2, 3, 4 and 5. Here the point 1 is the starting point when the load is applied on the material, tensile load is applied on the material, up to point 2. After the point 2, there is a permanent deformation takes place, and below the point 2, after the removal of the load, the material regains its original shape. That region is known as the elastic region. And beyond the elastic region, beyond the point 2, if it is deformed, if the load is applied, the stress increases and proportional to the strain up to point 3. That point 3 is known as ultimate tensile strength or tensile strength of a material. And still, if the load is applied, it beyond goes up to 0.5, the fracture takes place. That fracture, that is sigma, that is if it is related to 5, that is the fracture stress. And here there is a slope. Here that slope, if we observe, the slope gives the modulus of elasticity. The slope is the stress. Slope equal to stress by strain. That slope indicates the modulus of elasticity or Young's modulus. So that sigma is proportional to the strain, sigma equal to E times epsilon, that E equal to stress by strain, sigma by E. Now here another is that here that is sigma by E at point 2, the modulus of elasticity is the yield strength sigma y by difference between epsilon 2 minus epsilon 1. epsilon 2 is here at point 2, epsilon 1 is the initial. The difference is epsilon 2 minus epsilon 1 is the modulus of elasticity at point 2. And there is a distance and elastic region, the slope, that is Young's modulus elasticity, and plastic region, the maximum strength. You can see the plastic region. The plastic region begins from after yield point 2 to point 3. That region is the plastic region. In the plastic region, there will be a permanent deformation takes place even after removal of the load also. Even after removal of the load on the component, the material doesn't go back its original shape. It remains the same. That is called permanent deformation. Now, if you understand the elastic region, in this elastic region, the material will return to its original shape after the material is unloaded or the removal of the load. It is like a rubber band. And in this, the stress is linearly proportional to the strain in this region. The stress is linearly proportional to the strain, that is sigma equal to modulus of elasticity times epsilon, that is a strain. Then E equal to stress by strain, where sigma is the stress and E is the modulus or elastic modulus or modulus of elasticity. This the stress also in SI units Newton per meter square, and modulus of elasticity is Newton per meter square, and whereas the strain meters per meter, that is no unit, the unitless. Now this point 1 to 2, then point 2 is the yield strength. It is a point at which the permanent deformation occurs. It is a point at which the permanent deformation occurs even after the removal of the load. If it is passed, the material will no longer return to its original length. So that region is known as the plastic region, begins from point 2 to point 3, and point 1 to point 1 TO2 point 2, it is the elastic region, where in the elastic region the material comes back after when the material is unloaded, it regains its original shape. Now, and coming to the elastic range, what is the elastic range? This elastic range means, if you understand, the strain or elongation over a unit length will behave linearly. That is the equation, that is y equal to mx plus c or mx plus c or y equal to mx plus b. So that's predictable, and the material in this elastic region, elastic range means or elastic region, the material will return its original. That means at the point 2, the material is unloaded. It goes back to point 1 once the applied load is removed. So the stress within this material is less than what is required to create a plastic behavior. So within this limit, okay, this elastic stress is always less than the ultimate tensile strength, ultimate tensile stress. Now coming to the description of point 2 to point 3, that is a region, plastic region. From point 2 to point 3, that region is known as the plastic region. This region, if you completely, is known as the plastic region, and this region is the elastic region. And it is a plastic region. So this point 2 to 3 is a plastic, 1 to 2 is elastic. Now in this plastic region, if the material is loaded beyond the yield strength, the material doesn't regain and will not regain its original shape, even if the material is unloaded after point 2 to 3. And in this, it will have a permanent deformation, not some permanent. It is a permanent deformation. And if the material is unloaded at point 3, the curve will proceed from point 3 to point 4. Instead of approaching, what will happen? Point 3 to point 4, that curve will approach. The slope will be, is the slope between point 2, it is the same slope between point 1 and 2. The distance between points 1 and 2, points 1 and 4, that is the distance between the points 1 and 4. What is the distance between point 1 and 4? Indicates that it is a permanent deformation. That is known as the strain hardening. So what is the strain hardening? Once again, suppose if the material is unloaded at point 3, it doesn't go back to point 2, to original shape, or point 1. It will go back to the curve, that is the fourth point. So the distance from point 1 to 4, it is indicates the permanent deformation. Now this permanent deformation causes what will happen? Okay. Now again, if the material is loaded again at point 4, from point 4, then the curve will flow back to point 3. The same elastic modulus and slope. So the material now has a higher yield strength of 0.4. This phenomenon is known as the strain hardening. So raising the yield strength by permanent straining the material is known as a strain hardening. This is one of the technique in order to increase the strength of a material. That phenomenon is known as the strain hardening. Strain hardening. Again here in this figure, when the material, once again, at point 2, if the material is stressed, if they remove the rod and if the material is unloaded, it go back to original shape, to point 1. That is the yield strength, or it is known as elastic region, elasticity. Still the load is applied point 2 to point 3, and here the point 3 is unloaded. Here the material is unloaded. Instead of going back, it doesn't go back to point 3, it goes back to point 4. Now it goes back to point 4. Still the the slope remains the same between point 1 to point 1 and 2 and point 3 and 4. The slopes of these two lines remain same. Still the load is applied. If the material load is applied, it reaches to point 3, go back. Then the yield strength will be increased. The process of this increasing the yield strength of the material is known as strain hardening. So within the same elastic modulus, it will flow back to point 3. When the material is loaded again from point 4 to point 3, it go back. Now this material now has which strength? Higher yield strength of point 4. Raising the yield strength by permanently straining the material is known as strain hardening. Raising the yield strength by permanently straining the material. Now before region here, applying the load, this is the first. Up to point 3 is the permanent deformation between point 1 and 4. But in order to increase the strength of a material, if the material is loaded again, so immediately it goes with the same slope of between point 1 to 2, the same slope with the same elastic modulus, the strain increases, permanent strain. Okay, that phenomenon is known as the permanent, that is known as a strain hardening. It increases the raising the yield strength by permanently straining the material is known as strain hardening. Now next, what is the tensile strength of the material? Generally people think that there are various points are there: yield strength point, ultimate tensile strength, and fracture strength. So which strength value of the stress value are considered as the tensile strength of the material? The tensile strength of the material is considered at ultimate tensile strength. That means our ultimate tensile strength is the tensile strength of a material. The largest value of the stress on the diagram, that is ultimate tensile strength, is the largest value of the stress on the diagram. That stress is known as tensile strength or ultimate tensile strength, UTS. Okay, and one more thing. this tensile strength, what is happening? The maximum value, the material can withstand at this value without breaking. Then what is the description of the fracture point 5? Here in this diagram, if the material is stretched further beyond point 3, the stress decreases. At that time, still increasing, then what happens? The necking formation takes place in the material. So that point, the stress decreases as necking and uniform deformation occurs. So fracture will finally occur, which point? That is the point 5. That is called fracture strength of a material. So the tensile strength of the material means it is not yield strength or it is not a fracture strength. It is the strength of ultimate tensile strength of a material is the tensile strength. So it is the maximum strength or maximum stress which the material can support for not to failure, for not to break, without breaking. So that value is known as the tensile strength of the material. Okay. The next, this is the practical stress strain diagram of a A36 steel. So we can see it is experimentally drawn or experimentally occurred results under UTM, Universal Testing Machine. So it is the elastic region and it is the yield strength, it is the plastic, and the strain hardening is taking place and it is necking down, and ultimate tensile strength, it is the fracture. It is the fracture strength. So the stress versus strain diagram. So various materials we can understand. That stress strain diagram is different from material to material. For copper, it is different. For steel, it is different. For brittle materials, it is different. So this is the stress strain diagram of A36 steel. Suppose if we consider any brittle material, the stress strain diagram will be direct without. So direct to fracture, there is no strain, that ultimate tensile strength and all. Here, the ultimate tensile strength for brittle materials, ultimate tensile strength for a bit of brittle materials is same as for fracture point and ultimate tensile strength. Both are same in the case of brittle materials. There is no deformation, permanent deformation here, and here directly fracture takes place. Whereas for ductile materials, we can observe there is increasing the strain. Now, the stress strain diagram is useful for studying the behavior of the material and also material properties. Here, the material properties or the characteristics of material properties are described as strength, hardness, ductility, brittleness, and toughness. These are the 5 prominent material properties which can be studied from stress strain diagram. And stress strain diagram, some of the things here, toughness can be studied from impact strength, impact testing. So what is strength? Here strength is defined as it is a measure of the material property to resist deformation and to maintain its geometry under the application of normal loads and also shear loads. Or here the normal loads again comes into the two. One is compression, another one is tensile. Under the either tensile load or compressive load, the strength means resistance to deform and to maintain its shape. That is one of description about the strength. Another one is it is quantified. How to quantify, how to measure the strength? It will be quantified in terms of yield stress or ultimate tensile stress, that sigma ut or sigma y. And high carbon steels and metal alloys have higher strength than pure metals. And ceramic materials also exhibit high strength characteristics. But ceramics are brittle in nature. So we can see ceramics are brittle in nature and no deformation in comparison to ductile materials. Now next material property is hardness. And it is also resistance too. The measure of the material property, but having resistance to indentation, abrasion and wear. That is the main properties of hardness materials. So it is how it will be quantified, how to measure this hardness property of the material with the help of hardness testers. There are Brinell hardness tester and another one is Rockwell hardness tester. So by using this Rockwell and Brinell hardness scales, so we can measure the hardness property of the material. So what is the difference between hardness and strength? So hardness and this strength correlate well because both properties are related to intermolecular bonding. This is intermolecular bonding, both are correlated, but one thing is that a high strength material is typically resistant to wear and abrasion and also indentation. So this is a description about hardness. If we compare the hardness numbers, this hardness is measured with the help of hardness number. For example, it is the Brinell hardness means BHN. For hardness, for Rockwell scales, there is Rockwell C scale numbers are there. Now here Brinell hardness numbers for various materials we can see here. So for pure aluminium, it is a 15 BHN, and pure copper it is 35. The maximum BHN number, Brinell hardness we can see it in the material of diamond here, 8000. And it is the pure aluminium is the minimum, least pure aluminium. So if the Brinell hardness number is more, that means it indicates the hardness is high for that material. If the Brinell hardness number value is low, that means it is less hard. If the Brinell hardness number value is high, it is the more hard material. Another one in this, it is here list mentioned, titanium carbide is having the next hard material. So that's why this titanium alloys are Ti6 and where those material are less weight and more strength materials. So this here titanium carbide is 2400 BHN, whereas tungsten carbide is 1400. And this tungsten carbide material is used for cutting the tools as a tips, tungsten carbide tips, because the cost of the material is so high. So that material used as a tip for tool bits and used for cutting the materials. And one other one is called high speed steel. That is also, but generally this titanium carbide or tungsten carbide. Why shouldn't we use a titanium carbide? So it is not required to use titanium carbide material. So with the tungsten carbide material itself we can cut materials. That's why it is the tool bits are used for titanium, made of tungsten carbide. So why didn't we go for titanium carbide? The cost is higher. The cost more than the tungsten carbide. That's why the tungsten carbide material also costlier. That's why we use it as a tip. So we'll insert the tips for the tool bits and use it for cutting purposes, tungsten carbide. So the hardened tool steel is having, it is between 650 BHN, between 700 BHN. And 304 stainless steel, that is 250, and mild steel is at 120, pure copper is 35. And finally, pure aluminium, the lowest here BHN number in comparison to other materials. So these are the Brinell hardness, the hardness of some of the material we are denoted quantified by using Brinell hardness tester. Okay, and one more thing is that next important property is the ductility. This ductility is having, what is the ductility? Ductility is also, it is the measure of the material property, and main property of this ductility means what? Deformation. More deformation takes place before failure. And how to quantify it? It is quantified by reading the value of a strain at the fracture point on the stress strain curve. How to measure ductility? So what is the strain value in the stress strain diagram? Here the strain value for A36 steel at fracture point. From this measurement of strain at a fracture point, we can know the deformation, the fraction of deformation. The strain gives the fraction of the deformation. How to measure the original length? The fraction of strain equal to delta L by L. So this delta L, what is the change in length? That can be measured, and original length. So what is the length, actual length, and this delta L equal to epsilon times L. This epsilon can be measured at this point at the fracture stress, and with the help of total multiplication, then we can know the deformation, that is a change in length, deformation. So thus we can measure the ductility of the material. So ductility property can be quantified by measuring the strain value at the fracture stress. So thus we can quantify this ductility. And here ductile materials can be pulled or drawn into pipes or wires and other structural steps. So for example, what are the examples for ductile material? Here it is low carbon steel, pure aluminium, copper, brass, all comes under ductility, ductile materials. And whereas one more material, it is the gold and silver materials. Some more materials are gold and silver. These materials are useful for making the ornaments, gold and silver. So these are the examples for ductile materials. So the deformation for ductile materials for gold and silver are very high in comparison to higher materials. And how to measure? Next property is the brittleness. The brittleness, we can see the fracture stress limits of the fracture stress for both ductile and brittle materials. The strain in the case of brittle materials are very low in comparison to the strain of ductile materials. So the ultimate UTM, the ultimate tensile strength of brittle materials are higher than the ductile materials. And this brittle material, one of the inability is called deformation. So inability to deform before failure, doesn't deform. Immediately fracture, failure takes place. And it is completely opposite to the ductile material. That's why we have shown brittleness and comparison with the ductile material. Brittleness with compared with the ductile material. That's why here we can see the tensile strength, the ultimate strength of the material is higher in comparison to ductile materials. And the fracture also higher. And one thing is that the rate of strain is low. The strain is very low. And examples of these brittle materials. Okay, glass, ceramics and high carbon steels are the brittle materials. Ceramics and glasses. Now the final property of the material is the toughness. What is this toughness? The toughness is measured able to absorb the energy before failure. That property is known as the toughness. It is absorbed by using it is measured by using two methods. One is I-joint test. Another one is Charpy test. Charpy testing. So this Charpy test means ability to absorb energy under an impact load without fracturing. So this impact toughness can be measured by using impact testing machine, that is called CHARP test here. Here we are showing the CHARP test. In CHARP test, the tool or specimen can be placed here horizontally. Then the cutter will come hammer. The hammer is released. That hammer acts as an impact load. That load attacks the material, the specimen. Under the impact load, that absorbing the energy can be measured, how much absorbed on the scale. So this pointer is moved such a way that on the scale, that scale gives the reading of absorption of energy. So in terms of joules or joules pronunciation. So this position is the anvil, whereas another test is known as I-joint test. In the I-joint test, the specimen is kept vertical direction, hold in anvil, and the hammer comes and gives the impact load on the specimen, and it moves such a way that the reading, the pointer moves on a scale that gives the I-joint reading. So CHARP test gives CHARP reading scale and I-joint. There are two readings are there. Here outer scale or inner scale, one of the scale denotes the CHARP reading, another one is I-joint reading. Now the CHARP test is an impact toughness measurement test, because the energy absorbed by the specimen is very rapidly under impact load, and it converts when the hammer is at this position, we are going to release, it is having potential energy. When it released, that potential energy is converted into kinetic energy, and the kinetic energy released the impact load on that. According to law of conservation of energy, the potential energy is converted into kinetic energy, and again it comes back. Only one specimen, one chopping, one hit. So like that we have to, in order to find out the average value, so we have to use the maximum number of specimens or 5. So the potential energy of this striker or the pendulum before and after impact can be calculated from the initial and final location of the pendulum. Next, the potential energy difference is the energy it took to break the material absorbed during the impact, and the main purpose is to evaluate the impact toughness as a function of temperature. But here is the CHARP V test we measured here. So we are going to show you that the stress strain curve, the CHARP toughness with respect to temperature. For brittle materials it will be, and whereas for ductile materials is the transition temperature zone. This curve indicates the CHARP toughness versus the temperature, effective temperature. And CHARP V test, under CHARP test at low temperatures, the material acts as a brittle material, but not strong, and in order to break, little energy is required to fracture the material. At a high temperature, because temperature is increasing, what will happen? It behaves more, it is ductile and also stronger, and also greater energy is required to fracture the material. So the transition temperature we are going to study, we are describing the diagram, the graph. At low temperatures, the material behaves as a brittle and low strength, it absorbs. When temperature is increasing, the material behaves more toughness, here this toughness, and more strength is required to fracture. And transition zone, the transition temperature is the boundary between brittle and ductile materials. So the transition temperature is very, very important parameter in selection of construction of the materials. So these are the CHARP V test for high carbon steel and stainless steel. For CHARP V test energy, we can see here how the high carbon steel is moving, and it versus the temperatures. At minus 200, and it is increasing the temperature. At low temperature to high temperature, that is minus 200 to plus 200, the behavior of the material is ductile when it increases from low to high. And low temperature is the brittle, low impact strength. High temperature is the ductile in nature, high impact strength. So you can, if you keep on increasing, there is a limitation is there. If you keep on increase the material, what will happen? The melting point. So it is within the recrystallization temperature, the material should be tested. Now these are the stress strain. Next material important property is called fatigue. So it is the ability of the material to withstand under cyclic loading. That strength is known as the fatigue strength. Fatigue failure. The fatigue failure means the failure of the material under cyclic loads. Then it is known as fatigue failures. So it is the repeated application of the stress typically produced by oscillating load and such as vibration. Vibration means the load caused by due to vibrations or cyclic loads. So when engines are mounted on ships and all, the vibrations of a ship and the propeller and waves, those loads are known as cyclic loads. So suppose if you consider propeller planes, the propeller continuous, that means the material should have the strength of fatigue, that fatigue strength. That is important property. Next, maximum stress decreases as the number of loading cycles increases. So when the loading cycles are increasing, so there is a limit. This is the limit. This limit is known as endurance limit. If the material is under the operation of less than this endurance limit, the material have infinite life. Infinite life. If it works outside, then what will happen? The material failure takes place. Material failure takes place under non-infinite number of cycles. At number of cycles, failure takes place. So this endurance limit is a threshold stress which will not cause the fatigue failure for the number of cycles. That's why under this endurance limit is the limit where the material is under the cyclic loading, under infinite. The life of the material is infinity. That is the meaning. So what are the factors affects the material property? There are various factors affects the materials. First, number one is that temperature. Under temperature, increasing the temperature will decreases the modulus of elasticity, decreases the yield strength, decrease the UTS ultimate, decrease hardness, increases ductility, decrease brittleness. So temperature affects hardness, decreases. Negative effect is hardness, ultimate tensile strength and yield strength. Only one thing is that increases the ductility. And another important factor affecting the material is that environment. There are different environments. If it's sulfides and chlorines and oxygen and water, radiation, pressure, these factors also, chlorines also causes the material properties. So if it is in various, especially all this affects in form of corrosion. When corrosion affects the material, the strength of the material, hardness, ductility, brittleness, all yield strength, all will be affected. So that's why we have to consider while fabricating, we have to consider factors of temperature and environment when the component is fabricated with various materials. These two factors, one is temperature, another one is environment. What type of environment? When we are going to design the ships and selection of the material are considering for fabricating the ship, we have to consider the environment factor and temperature. When under low temperature, the material acts as a more brittle. Under high temperature, the same material behaves more ductile. So these materials properties are highly important. So there are, in order to, when these are affecting, how to change, how to alternate the material properties. So there are various methods are there. Mainly that alloying, another one is heat treatment or thermal treatments. So by using these two methods, we can alter the material properties. So in this session, we have studied what is a stress strain diagram. Stress strain diagram is highly useful in order to study the material behavior of the material and material properties. So we have studied what is a stress strain diagram for ductile material and also brittle materials, and also material properties. The material properties are brittleness, strength, ductility, brittleness, hardness, toughness, and fatigue. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.